Our next speaker is Jonathan Passerat-Palmbach. Jonathan is a researcher at Flashbots.
Thank you for staying. These talks about trying to map out something that we think could be new, Agentic MEV, so the term is a bit vague. We'll try to go through it, especially like in 3 directions. I want to first walk you through how today we can use AI for MEV. We'll see what it means. And then try to slightly shift towards how we start to see MEV-type behaviors in AI networks. So there's 2 distinctions that I make. One is MEV-aware AI, so typically like agents facing directly MEV-type scenarios. And what I think could be very interesting as well for the future, the new types of networks and new types of behaviors that we see emerging from how modern AI is being architectured. OK, so that's our plan for today. Let's start first with AI for MEV. So I find it quite surprising, personally, that especially like, with all the hype around AI, we don't see as much work trying to do AI for MEV, right? There is a bunch of papers, don't get me wrong. There's like some bidding games paper trying to apply reinforcement learning for bidding. There was like the block GPT paper as well. But you don't see that many. My guess is that the bottleneck is data. Quality MEV data tends to be gated behind private lanes. And we see it from the mempool being dried up. And clearly, the rich signals are proprietary. So that's maybe why we don't really see much AI being applied to MEV. So the interesting question is, like, what can happen when you have access to such data? Turns out we do. So one thing I want to introduce you to that you might have seen before is this architecture that we've started using for what we call parallel block building. So it doesn't mean that the whole block building process becomes parallelized, that you don't throw it on the GPU. But basically, you try to split your block building process into 2 phases. One, when you try to isolate the conflicts between transactions, so literally like 2 transactions touching the same state. You don't even need to know whether it's read or write. They just touch the same thing, so you think they're going to be conflicting. And you put them into these different groups. And the goal of the parallelization is to resolve the independent groups separately. So you gain from this aspect. And you can throw different algorithms at that. You can do something like very simple. If you've got a small group, you can try all permutations, for example. Or you can do some like greedy packing. You can even do random packing if you want. And once you've resolved all your groups, you just reduce your algorithm and bring all these things together into a single block. Okay, that's the premises for what we're trying to do. Now, what's interesting is that this step of resolving the ordering is something you can iterate upon and you can inject AI into, right? So, for example, you can try to use a genetic algorithm as long as you can define a fitness. Turns out we have one, the block value, for example, to try to optimize towards that. And that's something we've been working on. Like one of my colleagues, Luis, has a very nice presentation at FCC that I encourage you to go and watch, explaining how we can evolve strategies to basically build better blocks. It works extremely well on high MEV days, for example. So it doesn't work extremely well for all MEV settings, but like in high MEV days, it works extremely well. Another idea, you can observe that the EVM in and of itself is a simulator, right? When we build blocks, we simulate transactions. And so we can leverage that to try and like apply a reinforcement learning type approach to construct the blocks as well. So for those of you who've seen like all the lineage of work from DeepMind, like all the alpha something papers, it's very similar to what they do in AlphaZero and in AlphaDev as well, where you're in this single player type of environment, but you can leverage the self-play, which in this case is the EVM, to learn what potentially is going to be a good block. So you start to have this notion of like learning what could be a good positioning, a good ordering in a way. And once you have this thing, the next step, you probably have seen this thing as well, is to try and like throw some auto research at it, right? So couple of months ago, everyone was excited about Enric Karpathy showing this very simple loop in a way where it was letting an LLM iterate over a simple Python script. So in our case, what that could mean would be to have our loop, have our agent, in a way, take into account a reward function. So at first, it could just be the same objective that we had before, maximize the block value. But it turns out that if we want to be more accurate, because in that case, I tend to think about this approach as like having more degrees of freedom as the previous one. So you can really do many things. You can change the code itself. You're not bound to like a single algorithm anymore. You want to be a bit more conscious about the kind of constraints you apply. And you want to have like what we call a do no harm policy in a way to make sure that, for example, the agent is not going to evolve a policy that builds very good blocks, but that tend to be front-running or sandwiching transactions. So inherently, what appears is that you need to be able to handle multi-objectives. And in these auto-research loops, as far as I know, they're mostly targeting a single objective. So one interesting problem is to try and understand how we can adapt that to multi-objective optimizers in a way. And why that is even more interesting is that, as I said, if you try to apply these things, we've been trying to play with a little bit, turns out that the auto-research loop can rediscover sandwiches on its own. You don't tell it anything. You just tell it, build me the best block you can. So the reward in and of itself of block value is not enough. Right? And we've seen that before. There's other explainers trying to apply auto-research for kernel optimizations. The agent will try to find shortcuts. So if you don't really have these guardrails, that can be an issue. Two directions that can be interesting that are absolutely not verified, so take it with a grain of salt. If you think about it, the way LLMs are being trained as well, you have this notion of like do no harm, right? When they are being released, the frontier labs are trying to make sure they don't go into specific topics, prevent you from like trying to build a bomb, these kind of things. There's multiple approaches to do it. One of them is to try to reason about what you can see in the latent space of the model, right? And try to push as far away as possible from each other topics that you don't want to accidentally collapse together. So maybe one idea is to also observe the latent space of a block, for example, and try to detect what is a sandwich in this latent space, to implement some guardrails so that the optimizer does not try to cheat and implement these things. OK, the other reason why I wanted to show you auto-research is that inherently it's something that doesn't run on a single agent, right? It runs on a swarm of agents. And maybe today it runs on your single laptop on your machine, but very easily you can imagine that it's something that can scale across the internet, right? So you can have, those that are old enough to remember, you can have like a SETI-at-home type vibe of agents all trying to collaborate towards a big objective. And of course, if you split that into different tasks without too much of a coordination layer, the goal is to race, to be the first one to update the new best and potentially claim the rewards if there's any. So now the question turns from like, how do you search with an agent to how do you coordinate these agents? How do you resolve contention, right? If we've got different agents all across the internet trying to each provide what they think is the new best, how do you do that? Well, in machine learning, we've done that before. That's kind of like what the literature in like federated learning and collaborative learning tries to do. And the approach here is to merge the updates. So you keep everything that has been produced, and you try to combine a new update from that. But in that case, it's different. Everyone produces like a standalone solution, right? So you want to choose between these different things. And there are some networks, like Ensues, that have been trying to do that, but it's all in an honest fashion, right? Everyone is behaving, everyone is like contributing towards the same objective. Now, in a way, if you turn that into something a bit more adversarial, where potentially you introduce rewards, some new behaviors are going to emerge. And you don't even have to go to something very adversarial in a way. You can even just look at this diagram and think about what differentiates these four agents. Potentially nothing, unless they have different GPUs. And in that case, what happens is that you morph into some kind of the rich becomes richer loop. Like if you have the best GPUs, if you have the best infrastructure, you will capture more value from the network, right? So that's something we've seen in the MEV space as well, where more sophisticated actors with like better servers, better connection speeds, more liquidity will capture more value if you don't pay attention to how you design these markets. So, some analogy here. And one way we've learned on how to solve these issues from the MEV space is that one thing that works pretty well if you want to avoid the race harder type of issues is to use auctions, right? So the question becomes, what would it mean to implement a top-of-block auction, sell the new best update to the best agent in the network? What would it mean to provide rebates from like a surplus of computation you've been not utilizing to obtain like your new result? So yeah, really open question of like, how do you implement auctions for that? I'm not going to solve that. Christoph will eventually. So another aspect that we need to be aware of when designing these agents, and that's very much in line with the previous talk, is who gets to see when you speak, right? If these agents also compete towards claiming a prize, you might have some incentives to censor communication or to behave differently depending on like who's going to speak next, right? So it seems that when designing these networks of auto-research across the internet, you want to be able to have some kind of a anonymous communication layer as well. So what Mark and Mateusz was presenting before is definitely not just for the type of applications we are used to dealing with. It can absolutely be applied as well for these kind of scenarios. Okay, so the last point I wanted to make during this presentation is to walk you through what I call AI MEV, so really like what MEV emerges from these AI architectures. There is no result in that one. It's just like a bird's eye view of like what could happen, so very much a live brainstorm with you all. I'm sure you know of the bit tensor network. That is split into different subnets, each of them permissionless networks, where you can join as a miner or as a validator to verify the work. They all like fulfill different AI-related tasks. One in particular, subnet 3 called Templar, aims to train a model across the internet, so decentralized training of models. But some other networks do fine-tuning, some do forecasting, so different features, really. Interestingly, these validators that have been staking, they are rewarded to agree with the consensus, okay? So a very easy thing you're incentivized to do is to skip the job and just align with what the majority says to claim the reward, okay? And again, if you do that, you tend to fall into a rich get richer scenario where the bigger stakers kind of like decide what is the truth into these updates. So people have been observing these types of behaviors, and there's a few proposals that emerge to try and address it. One is called proof of learning, where you force the updates to come with not like a ZK proof, but more of a trace of the training protocol. It has shown to be a bit fragile. You can very easily change these traces and still get away with it. So another approach would be some kind of like commit reveal, where before resolving the scoring, everyone has to commit, right? But in that case, we fall back into the kind of dynamics that we know, because the game becomes a latency race again, which is the first to reveal will be able to adjust the strategy, okay? So we also need to be a bit more clever into this type of networks to, once again, reapply the MEV playbook to design better systems. And that goes even further. You, I'm sure, have been aware of like all the work we've done in the past. My colleague Barak has been publishing papers on cross-domain MEV, for example. And so here we have these different subnets, okay? And each of them behaves like an AMM, okay? And the network's token, the Tau token, is distributed across all of these subnetworks based on their activity, right? So there has been work showing that on a specific subnet, the miners could like pump, in a way, the activity in the network to claim a bigger share of the broader distribution, okay? So again, from the dynamics that we know from cross-domain MEV, we kind of like know how it tends to be like a centralization vector, in a way, where well-capitalized actors will kind of like be better able to coordinate across different domains, and again, gain better and better control of the overall network. So something we want to avoid in these cases too. A topic we talked about this morning with Danning's talk, prediction markets. Prediction markets most likely have and will have MEV. And in their case, the issue boils down to the oracle problem. If you remember one takeaway from Danning's talk this morning, it was pretty much that it's pretty hard to agree on how to resolve a prediction market, right? So it means that whoever has the control over this resolution, whoever is the oracle, has like an immense power over the prediction market in of itself. So there's most like, if we want these things to work, we need to work pretty hard on designing better resolution mechanisms for prediction markets. Interestingly, one approach would be, let's throw agents at that, right? Let's try to turn the oracle into a network of agents that provide indications about how a market should resolve. So you're a bit upstream of the resolution itself. And that's what the Numinous network, still on BitTensor, is trying to do. The problem is, for the validators in that case to rank the agent, to score them, they must see the submissions in clear, right? Before you've validated, before they have actually scored and committed to something. So literally, these validators have a strong incentive to take whatever update, whatever predictions these agents have been providing, and to set up their own miners or to collude with different miners. And what we see here is basically an example of pre-trade privacy that we've been trying to solve in the MEV space with programmable privacy, right? With TEs or some kind of like, FHE type of encryption, where you should be able to perform your function in the network, but without gaining an advantage by seeing what's the underlying commitment in the clear. The last one I wanted to bring up is more of an analogy we've been discussing this week as well. It is how, if you think about how the DeFi ecosystem is unfolding, with users expressing intents, sending them to solvers, the solvers like trying to find the best quotes to execute these intents, we tend to see something a bit similar these days with the AI networks, where I have my prompt and I can potentially try to send it to a router, right? And this router will just try to get me my reply for hopefully like the best price. Now, it's interesting to think about what happens when these routers become also actors in the network, right? With the emergence of like open weight models, for example, what if the router becomes so good or so incentivized to route all the traffic to their locally run open weight local model and capture the difference, right? This is again straight from the MEV playbook. So I don't know if we've seen anything in this direction play out just yet, but something to potentially like pay attention to in the coming weeks and months. To summarize this talk, really what we have is this progression towards, we currently are able to use AI for MEV, but as I said, only if you have access to the right type of data. There's potentially like one unlock to make this data available to more people, is to kind of like revive the direction of data clean rooms, where you're able to tap into sensitive data under specific constraints. MEV-aware AI, so this idea of like making our AI networks, AI agents more, making sure that they are designed in such a way that they are aware of like all the strategies we've been deploying. So think about auctions and everything we can borrow from mechanism design, for example. And finally, something that is more optimistic, or I don't know, like just more something that we probably will see in the future, this AI MEV emerging from how AI networks are being designed. And in that case, you can think about it as like MEV being captured at the application layer itself, and how to learn to design better AI networks so that they take that into account. So like these three layers. And I can also leave you with like clear research directions if you're interested in like throwing your agents to one of these topics and get a cheap paper out of it. Thank you very much for listening.
Just a quick weird question for you. Did you ever participate in folding at home or study at home yourself?
When I was 10, yeah.
Why did you stop?
I don't know, actually. Probably, it was super unreliable back in the days, and I had like a very not too powerful computer.
Okay.
So, yeah.
Great presentation. Thank you.
Thank you.
Additional questions?
Thanks, great talk. Going back to the first few slides, the slide about AI safety. So one method was mentioned was like restricting the space. But like for that, we need like good definitions of like what constitutes a malicious action versus an acceptable action by the AI agent. Like, do you think this could also be a potential part of the research agenda, like defining what constitutes a good action? Yeah,
very much so. It's it's kind of like what we have on the final point. Like there's the technical side of it, there's the philosophical side of it, right? We can all disagree or agree on like what is harmful versus harmless, and I don't think we will agree on something. What would be interesting though would be to have a clear way of expressing these constraints and these requirements, and then as a retail user, you can decide whether or not you want to go for like a block builder that has like some very clear rules. That's more the direction, I think.
Do you think it's easier or harder to define good and bad AI as good or bad MEV?
I think it's easier to define good and bad MEV, I think.
All right, we're screwed then.
Yeah. There's no such thing as bad MEV, right?
Jonathan?